money. I want to thank the organizers of this meeting for inviting me to give this talk, in particular to Mark for suggesting this topic that forced me to recover things from my starting point as a researcher. So let me show the general idea of the talk. I'll try first to motivate why to worry about Refinement monoids, and then I'll move to K-theory of algebras, that is the natural context in where you can consider that at least from a ring, as if you're a ring theorist as them. Then, because of the needs of using of this monoids in K-theory of rings, I'll explain you a little bit about the structure of refinement monoids and some applications. And then I'll move to a different context, that of type monoids of Boolean inverse semigroups, that it looks like different place to work with, but in fact, at the end of the talk, I will show you that all things connect in a very beautiful way. So I'll close with 2 sentences with conclusions, and there is some bibliography, since I'll share the slides with anyone that is interested. There is a lot of papers and books you can trace more deep knowledge of the topic. So let's go to the first motivation. So it sounds quite strange, but you're trying to understand, I'm a ring theorist, the structure of a ring, and then what you do is to use some trick. For example, representing this ring into rings that are very well behaved. I mean, for example, matrices over finite or infinite sized matrices over fields that will be endomorphism rings or finite dimension or infinite dimension vector spaces. You can extend the scope to endomorphisms of abelian groups, but in any case, having a representation of a ring as endomorphisms of groups is equivalent to consider their modular structure that you are defining by the representation on your abelian group. So essentially, understanding representations of rings is understanding categories of modules. That depends on the modules the representations you are interested in. For example, Kevin is interested in the irreducible one, so you need to look at simple modules over your ring. You need to restrict your attention to special subcategories. In the case that your category has representative with respect to some equivalent relation, for example, isomorphism, and in a small subcategory that is closed by finite coproducts, say finite direct sums, then you can encode the information of this category by looking at the monoid of equivalence classes of the elements of the subcategory, where the operation is the one induced by the direct sum, and the neutral element is the class of the zero module. So most likely, this will be the only invariable element. We will say that's a conical monoid, and it will be abelian because the direct sum of modules is commutative one. So examples of categories where that happens and that they are related to representations of rings. First one, this natural one, is finite dimensional vector space on a field that is related to finite dimensional representations of a ring. That is a good starting point for understanding the structure of a ring. But also you can extend that to finally generated projective models that are the finally generated models that admits a complement to a free module of finite rank, and that encodes the information about behavior of idempotence in matrix over the ring. So produce a lot of extra interesting information about the behavior of the ring, especially when the ring is rich in contents of idempotence. For example, real rank zero C-star algebras or graph C-star algebras are examples of algebras in which this kind of category is very important. But Mark is starting to be nervous. I want to talk about monoids, not about rings. Also, you can consider n-dimensional homogeneous Riemann space and with a volume, and then the action by affine isometries, and then study the polyhedra in this space by considering 3 different equivalence relations. The natural one is the congruence. 2 polyhedra are related if they are affine isometric, but also you can say extend that by taking an extra one, the decomposability, that says that your polyhedra has the same volume, and you can decompose in finally many subpolyhedra that are pairwise affine isometric, or even you can say stress a little bit more and talk about equivalent complementability. I'm sorry. I'm a Spaniard, you know? Okay. This is out of the other kind of examples, but I need you keep that in mind because this is the, say, inspiring example for looking at type monoids. So I'll come back later in this kind of so in any case, the object we will consider as a tool for our analysis of the structure we are interested in understand is a monoid. A monoid is an empty set with a binary internal operation and a distinguished element zero. And the operation is associative and zero is the neutral element. I'll say that is conical if it is the only invariable element, and it's commutative if so is the operation. So it's quite restricted with respect to the ones that appeared in Victoria's talk yesterday, but still interesting. And you can endow sort of ordering in this kind of monoids, the algebraic ordering, by saying that A is less or equal than B, even only if there is a complement C of A into B with respect to the equality and the operation. Okay. Coming back to the representations, when you're considering representations and you're, for example, you're Kevin and you're interested about the reducible ones, then you pick any representation and you pretend to write it up to some equivalence as a sum of finally many or infinitely many irreducible ones. But then the problem is that you can have two different decompositions that are related by the equivalence, but you don't know which are the relations between the say the reducible superrepresentations you're considering with. Then you need to get some trick that allows you to relate these superrepresentations. That, for example, happens when you're looking to finite dimensional representations. If you have, say, a decomposition like that, so two representations equivalent to other two, and then what you have is that comparison of dimensions say that you can decompose as a direct sum A in two subspaces and B in other two ones, that so that when you rearrange the additions in a different way, you can recover C and D. Essentially, what you have is, you can write that with a so-called Refinement matrix. A is isomorphic to the direct sum of these two subspaces, B to the ones, and then the horizontal sums recover C and D. So you can say relate these representations by finding a refinement of them in some small one that are into the A, B, C, and D, and help you to rearrange the information. And this is the idea of refinement that also occurs in the set of polyhedra when you consider the equivalence, the equidecomposability relation in the polyhedra. And but in general, if you're looking for finally generated projective modules on rings, then that doesn't happen in general. For example, even with very well behaved ring like the ring of real coordinates on the two sphere in the three-dimensional Euclidean space, this is a hereditary Noetherian domain. It's commutative, it's beautiful, but the problem is the Hairy-Ball theorem that says that essentially there exists an stably free, non-free projective module such that direct sum the free module of rank 1, you recover the free module of rank 2. That means that the monoid of isomorphic classes of projective modules on the ring is neither cancellative nor refinement. So natural question is, if you want to use this kind of idea of refinement, you need to keep track of in which circumstances you can expect to have refinement for your particular subcategory of the ring. In 1968, Crowley and Johnson considered a question in a more general setting possible, and then related the existence of this kind of refinement of equivalence decompositions to some sort of a change, keep the name in mind, property that is related to internal properties of the submodels or the substructures you're dealing with. And so our context is, we have a ring, we're studying the category of modules, and we are lucky, so we have representative of a small subcategory closed by some finite direct sums. So we have a monoid we work with. And the category has the refinement property. If for any identity like that, you can have decompositions as the one exhibited in the finite dimensional vector spaces. You can replace the isomorphism equivalence for other type. For example, in polyhedra, you have 3 different equivalence relations to be considered. So the definition of for us of a refinement monoid will be a conical commutative monoid, such that each time you have one identity like that, you can write down a metric such that A is equals the vertical, B also, and C and D equals the horizontals. So you have this kind of refinement. Okay. Fundamental fact that was shown by Hans Robert in 1963 is that any commutative conical monoid can be embedded in a refinement one. So essentially what you're saying, if you're interested only in the monoid as an abstract structure, is that when you have some kind of a arithmetical problem with identities in commutative monoid, you can put it in a refinement monoid. Perhaps there are tools that help you to get the solution to your problem. And then the problem is, say, as usual, to recover the information at the original place. But at least you can do that. And well, basic examples of refinement monoids is non-negative integers. That is a classical example of a commutative, as a cancellative refinement monoid. And if you take any abelian group at an extra zero, then this is not longer cancellative. It's remarked yesterday by Victoria, but you have a refinement monoid after. And I put these examples because they will play an important role in the applications of K-theory to in a minute. And but point is, this class is closed by taking direct limits, direct sums, products, and certain kind of quotients. And so it's a very well-behaved class that allows you to consider a lot of examples. And the point is, well, perhaps your monoid is not cancellative, so perhaps you will prefer to work with groups. You can do that. You can extend the definition to pre-ordered abelian groups, where you're taking an abelian group and a conical submonoid that generate G by differences. This generate so the group is directed, and you can endow an order using this submonoid by saying that X less or equal than Y, even only if Y minus X is an element of this submonoid that it's called the positive cone of the group. And then we will say that the group is refinement if SU is the positive cone. And for example, that happens when you have a cancellative conical commutative refinement monoid and you pick the Grothendieck group, the universal enveloping group of this ring, then you have here partial of the group that is refinement. This is a quite classical example. When you're working with rings, the way you will get a monoid that will be cancellative is taking in consideration that the ring has to have normally stable rank one. That's one of the reasons that even in sister algebras, there are some situations in which people consider restricting the attention to algebras of stable rank one, because then the monoid is cancellative and you have this kind of behavior. Okay. Hola. Okay. Okay, so let's see which kind of applications we can expect of that at the level of K-theory. Pasa este mando. Okay.
Hay que apuntar al ordenador, ¿no?
Vaya por Dios, pues sí que estamos bien. Okay, so K-theory, it's something that's a theory, some kind of, some sort of homology or cohomology theory that appeared in algebraic topology in 1940s and 1950s, but quickly was connected with ring theory and representation theory. If you recall Francesca's talk, she used say K-theory for spaces, but this is related to the K-theory for the corresponding continuous functions on these spaces that are sister algebras. So we're talking the same language in a different way. There are works of also in very more say abstract algebra theory of Ellenberg and Cartan, etc. And the general tools were developed by Heimann-Bass, and of course they originated algebraic homology and cohomology at the more category, more abstract level. The category we work with, so is that the finally generated projective model. So we are concentrating our attention in the K0 group that is one part of the full algebraic K-theory of algebras, but it's the one we are interested in. The basic objects, in this case of Bass K-theory, are the monoid of isomorphism classes of objects in the finally generated projective models, that is monoid B of R, and encodes the non-stable K-theory, that is because the relation is isomorphism, not stably isomorphism. And then you have the universal enveloping group of this monoid, that is the Grothendieck group of the ring, and that encodes the stable K-theory. The point is that name stable is because This is the preordered group generated by the monoid of stably isomorphism classes of elements. So you're taking isomorphism up to adding an extra thing that is common to both. Okay. So essentially, when you're taking as a generator the image of V of R into the group, and when V of R is cancellative, this is the positive cone of the group, and the group is partially ordered. And if the monoid is a refinement, so is the when the monoid is not cancellative, you lose things in translation. For example, you can lose refinement property. That's the reason people, when try to use refinement in groups, restrict their attention to stable rank 1 algebras. The initial example to understand what's the usage is that of dimension groups. Dimension groups is kind of partial order groups that enjoys essentially two properties. One is to be refinement, and the other is say imperforation that is sort of order torsion freeness. So for any x and y, and any n, nx less or equal than ny implies x less than y. The other direction is time. So it's like doctor 3, but related to the order, not only to the equality. Efros, Handelman, and Shin in 1971 showed that any countable dimension group, that is an abstract thing, is a countable direct limit of simplicial groups. So groups that are finite direct sums of copies of the group of the integers is order group. So essentially, you're saying that this abstract characterization comes to something like taking finite direct sums of that, performing any direct limit, and then you will get all the possible dimension groups. And in 1973, George Eliot used that in order to give the first result of classification of C-star algebras. He showed that any countable dimension group is a K0 group of suitable AF C-star algebra. If you move to the ring, general real theoretical setting, it's a suitable ultramatricial algebra over any division ring, if you prefer. And moreover, he showed that in these classes, the order K0 group is an invariant that classifies. So if you have unital AF C-star algebras, they are isomorphic if and only if the order K0 group with order unit is isomorphic. Not only that, I'll skip that part, but also you can faithfully describe the ideal theory of your AF C-star algebra just looking at the behavior of the so-called order ideals of your group. So all the information of the algebra is encoded in the group. That's really interesting. And this is the starting point of the so-called classification problem that not so later George Eliot provided to all us, saying, okay, perhaps for some special subclasses of C-star algebras, you can give invariants for classification related to K-theory, say the K01, the K1, the space of quasi-traces, etc. Finite collection of invariants, easily computable, that allows you to say not only that the algebras are isomorphic or not, but also gives you some extra information about the internal structure of the algebras using a more easy tool. Say, I mean, C-star algebra is more complicated than a Wheeling group. That's clear, isn't it? Okay. Another class where the B monoid is refinement is that of pure infinite simple rings. Natural question, what's that? Okay, it's a ring that is not a division ring. And whenever you have A, an element different from 0, A, there is X and Y such that X, A, Y equals 1. So in particular, unital, pure infinite simple C-star algebras are examples of that. There's a non-unital definition, but I'll skip that. In any case, in this case, it's very easy to show that the B monoid of the ring is the union of the K-through group with an extra neutral element. So it's not cancellative, but almost cancellative. And the most important thing, not even refinement, this monoid encodes the stable K-theory. So they are almost the same thing. It's not completely related, but recall Kirchberg and Phillips independently in 1995 showed that the pair of the K0 group and the K1, that I'm skipping who is an invariant that classifies separable nuclear, purely infinite, simple in the UCT C-star algebras up to as isomorphism or Morita equivalent, depends if the algebras are unital or not. In fact, they show that this invariant stresses all the possible values. So it's quite interesting. At this point, it's curious, the two classes that I presented, that they are classifiable as a refinement monoid. So the questions, quite natural, is what kind of algebras or rings you can expect the V monoid being refinement? And second one, when you have such a class, which kind of information you can expect to represent as faithfully as possible in your class? Because if you represent as a refinement monoid, but then the information is a crap, who cares? Okay. So for answering the first question.
Wait, sorry, can I ask a question about the
Yeah,
box
sure.
quiz on the previous slide?
Yeah, right.
Is there a way to like take the J0 and J1 and like actually do that? Or is it just like,
You take any pair of countable abelian groups, and then you can say guarantee that there exists up to isomorphism a unique separable nuclear polynomial infinite simple C star algebra in the UCT, such that the K0 is the G0 and the K1 is the G1.
but like as in can, or you literally can, like as in it's known that it should be possible, like, or is there like a way to?
Pretty explicit.
Yeah, okay.
You can use, for example, Katsura algebras that give you a pair of matrices related to the groups, the description of the groups as abelian groups, and using that you can write down a concrete algebra.
Okay.
Yep. Okay. Classes in which the monoid is refinement. For example, von Neumann regular rings. That is a class that was introduced by von Neumann in 1940s in order to give a ring of coordinates of continuous geometries, and the class includes a ultramatricial algebra, algebraic siblings of AF sister algebra, self-similar semi-primitive rings, continuous rings, a lot of families of rings, and also at the level of sister algebras of real rank 0 that they're introduced by Brown and Peterson, that includes AF sister algebras or purely infinite sister algebras, are also algebras where the V monoid is a refinement. These two classes, apparently disconnected, are included in the biggest one that, recall, a change rings. That was a class introduced by Bob Warfield in 1971, 72, related to Crowley and Johnson refinement properties as the rings of endomorphisms of finitely generated projective models that enjoys the so-called finite change property. But quickly, Goodall and Nicholson independently showed that there is a abstract characterization that is related to the behavior of idempotence that lives in right ideals of your ring. This characterization, I will skip to explain which is, allows to say automatically that fundamental regular rings are change rings. But with respect to real rank 0 sister algebras, we must respect to 1995 when Ara, Goodall, O'Meara, myself, showed that real rank 0 sister algebras are exactly the sister algebras that are change rings. So we are giving a completely algebraic characterization of a sister algebra property that is topological. Okay, that it's surprising. I'm still surprised of that. It's the most surprising thing. Another class that is not completely contained in the chain rings in which the V monoid is refinement is that of Leibniz path algebras and their algebraic siblings, graph sister algebras. And the advantage here is that you can compute directly the V monoid just looking at the graph. And then you can recover the case theory and all things works quite correctly. It's not so well behaved as change rings, but not bad at all. Now let me.
So Enrique,
yeah.
What is the reference 9?
9 is this paper of Ara, Goodall, O'Meara, and myself, 1995. 2 that says that purely infinite simple rings also are change rings is a reference of 2002, is a paper of Periara. That I think that the title is the change property in purely infinite simple rings is very, very descriptive. And that paper is a paper of Ara, Moreno Frias, and myself of 2007. That is non-stable K-theory for graph algebras, or I don't remember the title. I'm one of the co-authors. I cannot remember the title. That's my mind is like a Gruyere cheese. Okay, this is the classes I will, and then which kind of properties you can expect when the ring is an exchange ring. There's a lot of properties that are well behaved. For example, ideal structure. Recall the B monoid encodes the information about idempotence in matrices, but if you're working with a ring like an exchange ring, where there is a plenty of idempotence, say affecting the structure of the ring, then the information should be quite good. Let me first describe which is the monoid or object that replaces the idea, the notion of ideal. So we have a conical commutative monoid. Then an order ideal will be a submonoid that is hereditary by the algebraic ordering. When you have an ideal, then you can define naturally an equivalence relation and then quotients. And the point is that when the monoid is refinement, then so are the order ideals and the quotients, and the lattice of order ideals of the monoid is so the set of order ideals of the monoid is a lattice with the sum of it and the intersection. This in general is not true. Okay, when you move to exchange rings, then what happens is that for any two-sided ideal of the ring, the V-monoid of the ideal is an order ideal of the V-monoid of the ring, and this construction keeps track of the quotients. Not only that, there's a surjective lattice homomorphism from the ideals of R to the order ideals of the V-monoid that is an isomorphism in the case of either Von-Neumann regular rings or sister algebras of real rank 0. And in the case of Levi-Path algebras in codes, which is the structure of the graded ideals, and in the case of the graph sister algebras in codes, which is the structure of the closed gauge invariant ideals of your algebra. So when, for example, any vertex that is in a loop, it's falling into loops, then they are real rank 0. You are recovering all the structure of ideals of your graph sister algebra just looking at the graph or at the monoid. That is quite interesting. Also, notion of stable rank, that is a notion about, reduction of matrices on the ring, and that affects some, in some sense, properties of cancellation properties of the modules. I'm talking about base stable rank for rings, but for people of sister algebra, don't worry. Rieffel's topological stable rank coincides with the base stable rank when the operator algebra is a sister algebra. This is a result of Blue-Wasserstein of 1974, something like that. And then the point is that the stable range is reflected in weak cancellation properties of final projective models, as shown by Warfield in 1973. But it's more precisely defined the relation when the ring is an exchange ring, and it can be easily described in terms of weak cancellation properties of elements in your monoid. So stable range of corners of your ring are related to behavior of some cancellation properties of the elements on your monoid. That is quite okay. And also, if you're interested in multiplier algebras, so you pick a several non-unital real rank 0 sister algebra with the stable rank 1, so the V monoid is cancellative and refinement, then you can recover the V monoid of the multiplier algebras that is not longer a real rank 0 sister algebra in general by looking at the monoid of intervals of this monoid. That it turns out to be refinement again, and you can even represent it as a fine lower semi-continuous functions of the space of states of this monoid on the positive reals. So in particular, you can use this picture as a monoid of intervals of this monoid in order to describe faithfully the ideal theory of your multiplier algebra, just looking at the monoid P of A and its monoid of intervals. This works of Ken Goodall, David Handelman, also Frances Pereira, etc. So it's, in fact, several relevant questions on the structure of exchange rings can be traced as properties in the monoids. For example, this dichotomy problem for simple rings that asks if rings in this class that are simple are either stably finite or purely infinite, or questions about the possible values of the stable range, and they're connected with say, purely monoid theoretical property that is called separative cancellation. That is easy to be recalled. Conical commutative monoid separative. Whenever you have A plus C equals B plus C, you can cancel C from the sum if C is living in the order ideal generated by A and in the order ideal generated by B. In semigroup theoretical terms is separative if all the Archimedean components are cancellative monoids. This is the definition that I think Clifford and Preston give around 1950. So it's a null tool of semigroup theory that plays a major role in problems in ring theory since the 1990s. So keep track of that in your mind, because that's important. Brookfield, one student of Ken Goodall, showed that you cannot expect all the refinement monoids to be separative. In fact, that's false, but at least the primarily generated ones are. Primarily generated monoid, say prime element in a chemical commutative monoid is someone that behaves like a prime integer with respect to the order. And monoid is primarily generated if any element is sum of finally many primes. By the way, if the order relation is antisymmetric, then the primitive generated monoid is so the primarily generated monoid is called primitive monoid. All of them are refinement. So this is just to get in mind what's meaning that. Brookfield showed that any primarily generated refinement monoid is separative, in particular because the monoid is refinement. Finally generated refinement monoids are separative, and then so are the direct limits of them. That is what they are called tame refinement monoids by R. and Goodall. And this is the class in which the community of exchange rings concentrate their efforts during the last 20 years in order to keep track, if you can at least represent that and keep control of which subclasses of exchange ring has monoids of this class, then you can have some chance of giving some approach to the answer to this kind of problems that are related to the separativity cancellation property. That carries us to the natural point of we need to understand which kind of monoids, refinement monoids, can be represented as V-monoids of exchange rings. Once you have the list, you can say if all them are separative or not, which are the extra conditions, etc. This question was posed, say, publicly by Ken Goodall in 1994 in a ring theory conference in Padua. So it's almost 30 years old problem, still open. And in order to answer this problem, it's necessary to be able to describe how to construct refinement monoids, at least primarily generated refinement monoids, in some sort of construction that you can retrace to the level of rings, construct rings, and get some result. Okay, and this is the structure problem for refinement monoids that I'll try to answer to. Okay, to you. It's not pointing to the computers, that is slow. It's like me after dinner. Okay, so what we try is to describe very essential classes of, say, primarily generated refinement monoids, present in abstract terms as expressions associated to constructions in terms of basic building blocks. Essentially, the idea is describing like dimension groups as the direct limits of simplicity groups. Essentially, this is the same idea. First class. Well, first I need to recall some definitions. Given a canonical commutative monoid, we will say that an element is free if n plus 1 times x is not less or equal than nx. That is regular if 2 times x is less or equal than x. That will be properly infinite in terms of projections. Idempotent if is 2 times x is x. An atom that I don't know what I put it that because I don't use means that there are no non-trivial decompositions of the element in terms of subelements. Then first class that was described in terms of construction was that of primitive monoids. It's a result of Peirce. I assume that it's older, but the only reference I am able to trace is from 1986. I don't know. In any case, what he says is that if you have any primitive monoid that's a Refinement, this is represented by fixing a set I subset with an antisymmetric transitive relation, and then your monoid, come on, man. Okay, your monoid is the monoid generated by the set with this kind of relations related to when an element I and an element J are related through this antisymmetric relation. It's easy to see that it's the same as giving a poset with a partition in free and regular elements, where free elements corresponds to elements that are unrelated to themselves by their relation, and the regular elements correspond to the ones that are related to themselves by the relation. And using the second picture, you can show that they are all direct limits of finitely generated refinement monoids, so they are 10. This is a result of Ara and Goodrell. Now you can pass to primarily generated regular refinement monoid. Regular means that every element in your monoid is a regular element. 2 times the element is less or equal than the element. In this case, this is a result of Dobertins of 1983. You can describe this monoid as the similarities of groups. So here you have the similarities, they're important. Then here you have a family of groups that are the Archimedean components of your monoid. And then there is a family of group maps connecting elements that are related by the ordering. Essentially, what you're doing is to pick the idempotence of your inverse semigroup. Yes. Similarities, then you patch the Archimedean components that are the groups, and then you show how to connect that through maps in order to describe how to adapt elements that are not in the same Archimedean component, but they can connect at some point. Essentially, this is the idea, and this gives you a complete description of say regular monoids in terms of this structure. And when the monoid is refinement, what he showed is that the similarities is distributive, and plus other extra few properties, he performed a construction quite related to the one I showed before, and he recovered any regular refinement monoid that is primarily generated by similarities of groups, and conversely. Okay, there's another alternative description that appears in a paper of Baron and myself in 2006 that says that essentially a regular revealing monoid, no restrictions about primarily generated, is refinement if and only if the monoid, the similarities of groups, the similarities of idempotence is distributive, and then the group homomorphisms appearing in the picture of Dobertins enjoys what's called the Mayer-Beatrice property, that is sort of rigidity in diamond diagrams, community diagrams of groups that are appearing in this construction. It's a little bit technical, but you can use that. In fact, we use that, and I'll say a few minutes from now, to give some abstract descriptions of monoids of some classes of algebra. And it is shown in an unpublished note of Fred Baron and myself that all conical, not primarily generated, but all conical regular refinement monoids are direct limits of finally generated refinement monoids also. So all them are separable, separated. And well, but what about all the primarily generated refinement monoids? This from expected till 2016 that finally Periara and myself were able to realize that you can stress somehow Dobertin's construction. You cannot talk about similarities of groups, so there is not similarities, and there are no groups as Archimedean components. But even though you can do the work by considering what we call an I system. What's an I system? You pick a poset and you divide in free and regular elements, and then these are, say, the elements. The poset is the place where you will patch your Archimedean components in your monoid, and then the Archimedean components are set to the elements in the poset, and it's given by a family of abelian groups. When the element is regular, then the monoid you're considering is a group, while and this is natural, because if the element is regular, then the Archimedean component must be a group. While if the element is free, then you can expect to be cancellative if it is separative, the monoid, but you cannot expect to be a group. So we take the direct product of the naturals with a group. These are the Archimedean components we are patching, and then we need to describe the maps that are connecting them. And this is quite involved because the maps are going from the MI to the group GJ, not the MJ, and there must to enjoy a lot of technical issues, horrible list of, in order to be sure that the monoid that you produce, it's a refinement monoid. When you do the direction of a I system to producing a refinement monoid, you have no restriction of it's primarily generated or not. But for taking a refinement monoid and producing a system that allows you to work with that, the restriction of a primarily generated, it plays a major role, so you cannot skip that. But you have a duality between primarily generated refinement monoids and say primarily generated I systems. that allows you to represent all them. Of course, the description will recover Pierce's and Doberton's results. And moreover, and this is the interesting part, because of this picture, we are able to characterize which finally generated refinement monoids can be represented as the monoids of Levy's path algebras. So we solved the representation problem not for a chain ring, but at least for Levy's path algebras in the case of finally generated refinement monoids. What's not so bad. And using also this result I said before related to Doberton one, our description of a primarily generated regular refinement monoids, you can describe by an abstract characterization of regular refinement monoids that are direct limits of direct finite sums of monoids of the form cyclic group plus one extra neutral element. So you can describe in a very abstract form which say the monoids of algebras will be associated to algebras that are direct limits of finite products of Kunz algebras. Now, Mark's still getting nervous because lots about rings. What about my Boolean inverse semigroups? Let's go. So I'll recover the example about polyhedra. I'll tell you about that. The type monoids. If you recall the example, we have polyhedra in a homogeneous Riemann space with a Boolean form, and we consider the monoid that is this polyhedra modulo the with the composability equivalence relation, and then it's known that is a refinement monoid. It's quite a little bit more difficult, but it's also known that it's cancellative. What this means is that in using this idea of refinement and cancellative, you can show that two polyhedron are equidecomposable even if they are equicomplementable. And this is Seiler's theorem, a classical theorem that is a partial affirmative answer to third problem in the list of Hilbert. So this kind of idea, Seiler's theorem is shown in different ways, but essentially this kind of idea says that you also can use refinement monoids in another places of the mathematical world to say something about problems. This
What was equi-complementable?
Equicomplementable means that you take two polyhedra of the same volume, and then you can take families of polyhedra so that you are adding those to each one of the other polyhedra, and then they are pairways. Well, the whole bunch is congruent.
Okay. Thank you.
Yeah, thank you to you. I never go the definition, but mine now is hard. Okay, you can extend that, and that was people in the topic did to construct monoids of equidecomposability types of Boolean rings under a group action, and you can, as they did Hans Dobertin in 1990s, to try to understand abstract measure theory valued with that's related to varieties of Boolean algebras, valued and refinement monoids, that is the kind of monoids he worked with before. And the conclusion is that then what you get in a more extensive way, when you try to say ball up all things that are unnecessary, what you get is the notion of time monoid of Boolean inverse group. That is a generalization of the previous one. This relation appears in Wally's PhD thesis, but also Daniel's papers reflect that, and some papers of Lawson and Scott do it. So essentially, that monoid is an analog for Boolean inverse semigroups of the B monoid of a ring R, but also appears related to the Berung's dimension monoid of a lattice. Fred Berung's is a lattice theorist, but he was obsessed with representation problem for finite regular rings. That's the problem of relating with people that is working in ring theory, get ill. And then he developed a notion of dimension monoid for lattice that helped us to give some very interesting results about the problem of the representation of finite regular rings in a purely lattice theoretical terms. I strongly recommend to, if you're interested in that, look at the ideas that develops Fred. I mean, Fred is a very brilliant mathematician. His imagination has no limits. I need to introduce the start of this section, and I need to recall what's a Boolean inverse semigroup. So you remember Alejandro's definition of Boolean inverse monoid. So you pick out the neutral element, you put a zero. Okay, that's it. So let's go. And now let me show who is the type monoid of a Boolean inverse semigroup. It's a commutative monoid freely generated by representatives of the idempotency of your Boolean inverse semigroup with the relations. The representative of zero is the zero of your monoid. Whenever two elements are found, say Murray von Neumann equivalent in the inverse semigroup, then the representatives in the type monoid are exactly the same. And it encodes decompositions of idempotence in direct sums. So this is the type monoid. This is our dramatic personae. And then following facts you can trace in a monograph of Fred Behrens about Boolean inverse, type monoids on Boolean inverse semigroups and applications. If the monoid is a Boolean, so if S is a Boolean inverse semigroup, then the monoid is a conical Refinement monoid. Not only that, but in some sense is well behaved because it has this sort of a cofinality property in the representation that implies that the type monoid defines a functor from the category of all Boolean inverse semigroups with additive semigroup homomorphisms to the category of all conical Refinement monoids with monoid homomorphisms. So you're transferring the information. This monoid, as in the case of the B monoid, preserves finite direct products and direct colimits. If you consider a group action on a Boolean inverse semigroup, then you take the type monoid and you can endow an action of the group on the type monoid, and then the quotient of the type monoid by the action turns out to be monoid isomorphic to the type monoid of this Boolean inverse semigroup that is a semi-direct crossed product of the Boolean inverse semigroup by the action of the group. And the description is quite explicit, so you can analyze group actions on Boolean inverse semigroups using this tool. And with respect to ideals and quotients, given a Boolean inverse semigroup, there is a there is a natural lattice isomorphism between additive ideals of your Boolean inverse semigroup and order ideals of the type monoid that, as in the case of the B monoid, keeps track of the quotients. So there is some parallelism with the B monoid of a ring, but also with the behavior of additive ideals of Boolean inverse semigroups in the context of non-commutative stone duality. This is a result of Alina and Mark, the very recent one, say 2019, 2020. Let me recall, Kristen showed that, but let me recall, when you have a Boolean inverse semigroup, you can construct the universal ample groupoid of S, either the one he presented or the one that Ben presented in his talk. And dually, for any ample groupoid, you can construct the Boolean inverse semigroup of compact open bisections of it. This is duality. Let's go, man. Okay. And it induces a dual order isomorphism between the set of additive ideals of the Boolean inverse semigroup and the set of closed invariant spaces of the unit space of your universal groupoid, such that whenever you have X closed invariant, the inverse semigroup associated to the restriction groupoid is the quotient of the inverse semigroup by the ideal, additive ideal generated by this space. And conversely, when you have the groupoid and you pick the groupoid of the quotient of this Boolean inverse semigroup by the additive ideal, then what you get is the restriction of the groupoid to the closed space associated to it. So in particular, in the case of this tagged groupoid that appeared in talk of Ben Steinberg, also somehow in talk of Chad, when you take the closed invariant subspace of filters, Excel filters, then the tag groupoid is not only the restriction groupoid of the universal by the closed space, but is the universal groupoid of a quotient of S that is a Boolean inverse semigroup with the property, and this is the magical thing, when you're looking at your representation of the inverse semigroup in the algebra, it encodes the multiplicative Kunz-Krieger relations that showed Lisa in her talk. So say the lists from 1 to 4 are multiplicative and they're related, but the fifth one, the additive one, in general Boolean inverse semigroup, it doesn't reflect. That's the reason of the appearance of tag representations and tag filters in Excel's work. But in this case, this Boolean inverse semigroup also encodes the additive property. So essentially, you do not need to look about the Steinberg algebra of the tag groupoid, only to the Steinberg algebra of the universal groupoid of this quotient that is a inverse semigroup algebra. So you can skip groupoids and topology and all that stuff. I know that sounds horrible for half of the people here, but I'm ring theory, so I'm trying to skip topology as much as possible. Okay. And now this is relevant because also if you look at any Boolean inverse semigroup, then you take the type monoid and you have a natural representation to the V monoid of the semigroup Boolean inverse semigroup algebra or any field. And as commented by Benz, this algebra is the Steinberg algebra of the universal groupoid, but then you join both the result of Alina and Mark with those of Ben, then what you get is that you can change the Boolean inverse semigroup and get directly a representation of type monoid of a concrete monoid into the V monoid of the Steinberg algebra of the type. So you can use this type monoid in order to try to figure out how to. This is more easy to be computed, more easy. And you can use this as a tool for try to analyze basic properties of the V monoid of the algebra and then try to compute the complete V monoid of this algebra. So it's a good tool to work with. And let me end this talk by briefly presenting two applications of type monoids to the structure of sister algebra and von Neumann rule rings. The first is a result of Raynon and Sims that says that essentially you have an ample groupoid Hausdorff. Then they use the type monoid to detect paradoxical decomposition of the groupoid, so the existence of infinite projections in the groupoid algebra. Essentially, what they took is minimal topologically principal ample Hausdorff groupoid, so the reduced groupoid algebra is simple. When the type monoid is almost unperforated, sort of weak unperforation property, then there is a dichotomy. The algebra is either stably finite or purely infinite. So they are using the encoding of the properties of paradoxical compositions in type monoid in order to facilitate a situation in which you can detect this dichotomy for simple algebras in a class. The use of this type monoid to detect paradoxical compositions also appears in papers of Ara and Excel or Ara and Matthias Locke that was remade by Kevin, that they analyze paradoxical compositions of by the actions of groups on spaces. Without the type monoid also appears in several papers, say papers about infinite projections in groupoid algebras of Astrid and Lisa, or also of Francesca, I think she has at least one paper in this direction. But the use of type monoid, it's the key point to encoding in a very easy way the information. The other one, we presented Perry and I 4 years ago here in a series of two talks. There's a result of Perry Ara, John Bosa, Aidan Simpson, myself, published in 2020, something like that, where we solved the representation problem of von Neumann regular rings for the case of finally generated Refinement monoids. And the strategy is quite a little bit involved, but first we pick a finally generated conical Refinement monoid, and then we extract which is his I system with this picture I gave before. Then we use the I system to construct a special separated graph. It's sort of generalization of the notion of a graph that it's encoding the CK2 relations, but not globally, but for partitions of the edges that are ranging in any vertex. And then they showed that we showed that this monoid can be represented as the monoid of this separated graph, that is the V monoid of the separated graph sister algebra. This is a result of Aranguderal. And then we use the relations arising from the I system to change a little bit this separated graph Levis path algebra to produce a new algebra with the properties that it contains a Boolean inverse semigroup such that The algebra is the Steinberg algebra of type group point of this inverse semigroup, and the monoid we have in starting point is the type monoid of this inverse semigroup. And then using that, and this is the most difficult part of the trick, what we did is to show that we can construct a universal localization of this Steinberg algebra that is a phoneme regular algebra, and such that the B monoid is the type monoid of the inverse semigroup. So at the end of the long day, you recover this monoid as the B monoid of the. And essentially, that's all. Conclusion: refinement monoids are almost everywhere, like mushrooms, and plays a role in understanding easily deep problems in various algebraic structures. And at the end of the long day, they connect. And that's really the end of my talk. So thank you very much for your attention.